All right, hello everybody, and welcome back to another week in aerodynamics class. This recitation is going to cover actually 2 weeks, week 12 and 13. Just given that week 13 is the holiday week, and I didn't really want to worry about filming recitation during Thanksgiving. So I'm going to be covering primarily what we touched on in the week prior to Thanksgiving break. I hope you guys are enjoying hopefully some time off and your transition to remote classes have gone smoothly. Just some housekeeping notes. Homework 9 was due last Thursday, the 19th of November. Obviously, the following Thursday is Thanksgiving, so we don't have a homework due then. Homework 10 is going to be due the following Thursday, which I believe is December 3rd. And I'll have to check, but I believe homework 10 is going to be our final homework for the semester because we have exam 3 and then after that the optional final immediately following it. So I don't suspect there to be time for another homework. But anyway, what were we talking about? We talked primarily about a continuation of our conversation on boundary layers. And we started off lectures with a pretty useful general diagram to always have in your head when you think of boundary layers. Boundary layers being defined as the height of the area above some surface in which the flow velocity is less than 99% of u infinity, as affected by the viscous dissipation from the wall. We can also define some thermal boundary layer with a similar definition that's generally higher, where the local temperature is within 99% or not within 99% of the ambient temperature. So generally when anyone mentions boundary layers, you kind of have this immediate diagram in your head, something growing over time or over distance. And from that, we did a quick review of a couple equations that were touched on, I believe, in homework 9, which was our displacement thickness boundary layer, which is the displacement caused by a boundary layer at some offset. So because there's a loss of momentum here, the streamlines upward then have to deflect upward. So we define the displacement boundary layer as such, and its mathematical definition is 0 to some y1, with y being the vertical direction, of 1 minus the local u, local v, or in this case u, and over the ambient pressure and density, density and velocity integrated with respect to y. Generally, u is going to be some function of y, or pretty much always u is going to be some function of y for you. And then we have the momentum thickness. Another boundary layer definition is given as same integral, just with a term in front of it. Oh, sorry. Got that one wrong. And at this point, you guys should be pretty comfortable with these as you've been asked homework problems regarding them. Okay, so the next thing that we got into in class is a pretty famous solution to boundary layers, which are specifically laminar boundary layers, which is known as the Blasius solution, which I think it was his PhD thesis in 1908. And it's essentially an ODE equation that uses the self-similar results of a boundary layer to define it in an easily, not easily, but a readily computable way. And I don't think we actually went over the actual equation in class because At this point in time, we don't use it generally. People like to just take Blasius's results as opposed to his solution itself. So it's a variable transformation. I guess I should go over that first, where instead of x and y, you make the transformation where y goes through this term eta, where eta is defined as y over u infinity u. So it's some slope kind of like this. And then f is some function of eta, where f prime of eta is basically the velocity term. So f prime corresponds more to velocity, which, so the integral of f is going to correspond to x. Integral of velocity corresponds to position. So yeah, let's go, x goes to f. So f prime is defined as u over u infinity, just the fractional local velocity. And so his overall solution is given as 2 f triple prime plus f times f double prime equals 0. And this is an ODE equation, and therefore it's solvable. There are some boundary conditions. Obviously, you're going to need those if you guys remember from DiffyQ. So the BCs are at eta equals 0, f equals f prime equals 0, and at eta goes to infinity. So as you go upwards in y, that's an eta, even though it's pretty ugly. F prime goes to 1, which makes sense. The velocity, once you expand past the boundary layer, this term's just going to go to 1, as your local velocity is going to match the ambient velocity. And so from this, you guys don't actually have to do these solutions. They're given to you both in the lecture and back of the book. But it's useful to kind of understand the equation in which we get the following results, which you guys will end up using quite a bit. And let's see. His more important results are his laminar boundary layer thickness. From Blasius, we get that it's given, sorry, this is a delta, is given as 5 times x, you know what x is, over the square root of Reynolds number with respect to x. And then we also have displacement thickness can now be given as 1.72x over square root of Reynolds number with respect to x. And then theta is 0.664x over the same RE with respect to x. So that's great. These are some very useful equations for you to know. We also have the integrated skin friction coefficient as, just cross that off, as equal to CF is 1.328x over, oh, sorry, just a constant, over the square root of RE. And all these are given in the laminar flow case. Empirically, this doesn't go from Blasius' solution, but the next topic we talk about is these same equations in turbulent flow. And it should be known that this isn't a solution. Instead, it's a best fit from experiments. It's empirical. So there's been a lot of data points taken over the years for these, and people have then used that data to fit a function to it and said, this is the equivalent solution. Blasius is an exact, this is an equivalent, but it's more than good enough for us. So the turbulent boundary layer thickness is given as 0.37x over Reynolds number with respect to x raised to the 1/5, 1/5. And then the skin friction turbulent is given as 0.047 over REX again to the 5th, 1/5. And so with these equations, you can now do a whole lot. If given a situation, you can determine whether or not you're in the laminar or turbulent regime, and then pretty much immediately back out whatever you need. Boundary layer thickness, coefficient of skin friction, displacement thickness, all that good stuff. So these are some useful equations and will be directly impacting the homework. So it's good for you to know it. So we then go on and talk about a specific flow situation, specifically the Coyote flow, in which simple Coyote flow, in which you have a wall here, wall there, bottom one's fixed, and the top one is moving at some speed UE. We know from solutions we get some velocity profile that looks like this. And specifically in the example that we go through in class, we're interested in what the temperature looks like with respect to y. So through this gap, what's the temperature doing? And so in the inviscid case, we were able to generate some equation where temperature of y, I won't go through the derivation, I'll just give you the result, is given as T wall, which is the temperature at the wall, and then TE is the temperature of the moving surface, is TE minus TW, so delta T multiplied by y over d, which is, this velocity function, basically. And so that's how you can find your local temperature, which is a pretty simple equation. And then we go on, so this is inviscid. If we want to do it viscously, so we're going to include the viscous dissipation term in our Navier-Stokes equations. This temperature function then becomes given as T equals TW plus your Prandtl number, UE squared over 2 coefficient of pressure multiplied by U over D minus, y over D minus y over D squared, end brackets, and your Prandtl number is just some dimensionless number in which it's the ratio of momentum dissipation over the thermal dissipation of the flow. So basically, how readily does inertia diffuse through the system, and versus how readily does a temperature gradient diffuse. So from that, you can determine whatever your local temperature of the fluid is in your Coyote flow. Okay, so I will, as just for your sake, I'll go over a quick intro of problems 1 and 2 for homework number 10. So for problem number 1, we have an airfoil that we're approximating as a flat plate at 0 angle of attack. You are given its chord length, and you are given U infinity. You're also given S. Temperature and density of air at that temperature. And what I'm asking you to do is plot what the boundary layer is over the length of the chord. But what's important to realize is that you guys have a couple equations. You have equations for boundary layer when it's turbulent and when it's laminar. So you then have to decide what regime you're in. there also is a possibility that there's a transitional regime, which I said ignore any transitional regimes. So in that case, it's going to be approximated as some step function. So along your plate, the Reynolds number is going to increase. You can have some transition where you're in the laminar regime and then you jump to some turbulent regime, which would cause your delta to increase. So what you have to do is go through, find out where or if you hit the critical Reynolds number at some core length critical, it's called X crit. And then before and after that, if this is the laminar regime, you're going to use your laminar boundary layer equation to plot that boundary layer shape, and then I'm asking you to connect that to your turbulent boundary layer shape. So you have to go through, determine where or if you're going critical, and plot the shape of your boundary layers from there. Additionally, I'm asking you to find CF if it's all turbulent. It should be, sorry, I'm not. I'm asking you to find, drag, which you can use your CF equations to then back out to. I'm asking for the total drag of the airfoil. So keep in mind that your CF equation is, a lot of people get tripped up where they take CF, calculate drag, and say they're done, but no, they've actually only calculated the drag of the top half. So keep in mind that you have to include both the top and bottom half if you're going to approximate an airfoil as a flat plate and you want to back out what the drag is. So please keep that in mind in order to find total drag. And then, then I'm asking you to repeat the same process for water. Only difference between water and air is a couple of properties, namely rho, the density, and the viscosity. So you guys have tools at hand to determine both of those for both air and water, and can do this process for both of them. Then problem 2, it is a temperature problem, so I'm asking you to plot temperature with respect to y in a Coyote flow. I'm not going to write down the equation because I just did, but I'm asking you to plot this over some length in the y direction that I give you. You should have all the information you need in order to generate that line. And then I'm also asking you to find the maximum temperature, which you can do by just taking the max of your vector that you generate if you're doing it in MATLAB. Or you could, get fancy with it, take the derivative, set it equal to 0, find out where the minimum is, like a minimize maximum function. But either way, it shouldn't be too hard to find some Tmax. And if you know the shape of what this line function will look like, the location of the Tmax will be fairly obvious to you. So with that, I think that's all I have to say to you guys for these weeks in Aero. Please, as always, contact me during office hours, and I hope you enjoy your break.